welcome to my channel. Okay, last lecture we discussed about intervals, partition of the intervals, okay, and norm of the interval. Today we will discuss about upper bound of interval AB. Okay, so suppose this is the real line one. Okay, there is a one interval like closed interval AB. Okay, so in case there are many numbers between A and B like x1, x2, x3 and so on, xn, xn minus 1 and this is xn. Okay, so there are also many more numbers greater than also B. Okay, so such as B is less than capital M1 or capital M, and M is less than another one capital M1, that is called another one great number. Here it is M, so here it is capital M1, again here it is another one number M2 and so on. There is a many more numbers which are greater than B. Okay, that type of number we can call upper bound of interval. So in this interval, maximum upper bound of this is B. Okay, so B is our upper bound. Why? Because B is less than capital M, which are greatest lower bound. Okay, greatest lower bound. Okay, sorry, greatest lower bound नहीं, least but upper bound, LUB, least upper bound. M is our least upper bound. Okay, so here these are all our upper bounds called upper bounds numbers. Okay, in between that we need to find least, that means least upper bound. Okay, least upper bound is our M. So this B number is less than capital M, which are least upper bound. Okay, and hence therefore B is less than or equal to capital M, that means the least upper bound. Therefore B is our upper bound of interval AB. Okay, same we need to discuss lower bound, right? Lower bound of interval AB. Lower bound of interval AB, right? So lower bound means again we need to consider same number line like A, B closed interval. There are many more numbers which are less than A. Okay, that means here it is, let's define small m1, small m2, small m3 and so on. Okay, so this is our lower bounds. Okay, these are all our lower bounds. Okay, in between we need to find greatest lower bound. So greatest lower bound means GLB, greatest lower bound. So m1 or A, we need to define A is greater than small m1. So small a is our greater bound of this interval, sorry, lower bound. This A is lower bound of interval AB, right? Because in between all these lower bounds, the GLB is A. So we need to define GLB as our lower bound, and here it is least upper bound is B. So we can define upper bound of this interval is B and lower bound is of the particular interval is A. Is it clear? Just because all numbers is less than A, so A will become greatest lower bound, that means the lower bound. Okay, this is the concept of upper bound and lower bound. So next we need to consider refinement. Okay, so after this partition we already discussed, partition of interval. Okay, I'll just take a review of this. Partition of interval means one interval is there, we need to make sub intervals like x naught, x1, x2, okay, x3, and so on, xn minus 1, and this is xn. Okay, these are our sub intervals. So next point is refinement of partition. Okay, so refinement of partition is usually denoted by p star. P star. Okay, so in case our partition like for example partition like 1 2 3 4 5, okay, then p star is our refinement of this. Means in this p star, that means refinement set, we need more sub intervals like 1 1 by 2, again 2, again 2 and 2.5, or you can say take 1.5, 2.5, 3, 3.5, 4, 4.5, and last 5. Okay, these are our some more elements in this set. So refinement means we need to refine this set by usual again subintervals, some more subintervals. So here it is, the definition of this refinement of set is P is subset of P star always. Okay, so this entire elements is already in the P star, so we can call P is a subset of proper subset of P star. Okay, so what we will discuss here, it is the subintervals are 1 2 3 4, but here it is more subintervals like 1 2 3 4 5 6 7 8, right? So that means in P star or refinement of partitions we get number of subintervals more than partition P, called, this is called refinement of partition, right? So after this, upper sum, sorry, upper bound, lower bound, partition, refinement of partition, and we already discussed norm of partition, right? So after this we need to discuss upper sum and lower sum. Okay, upper sum and lower sum of given function on interval AB. upper sum of upper sum of interval AB. Okay. Upper sum means here it is one interval. Let's say A is equal to x naught, and here it is B that is equal to, or xn is equal to B. Take. Okay. So we need to take x1, x2, x3, and so on. Here it is xr and so on xn. Okay, these are our partition of particular interval AB. Okay, so we need to take upper sum, means we need to take sub intervals like I1 is our sub interval 1. Can I define x0 x1 sub interval, I2 x1 comma x2, I3 x2 comma x3, and so on. Our ith right rth interval, that is xr minus 1 comma xr, and our nth subinterval, that is in equal to xn minus 1 comma xn. These are our subintervals like this. This is subinterval, this one is subinterval, this one another, and so on. This is our subintervals of this interval AB. Okay, so upper sum means we need to identify upper upper bound from particular intervals. Okay, that means upper sum. Okay, on that particular interval. Okay, so upper sum of this interval is x1, x2, x3, xr, xn. These are our least but upper bound, LUB, or you can call supremum. Okay, these are our supremum, right? The sum of supremum called upper sum. Okay, so we can define this like summation. Okay, so we can take sum of ir ir into xr. This is called upper sum of the interval. So with this same concept we need to explain upper sum of AB by using f of x. Okay, that means there is one function on interval AB. Okay, like this is our function. So we need to make partition of this function over the interval AB, like a is equal to x naught, x1, x2, x3, x4, and so on. Our xn is equal to b. These are our some partitions. Okay, and so on. Okay, so in between over this function f of x, we will get f of x naught here, f of x naught here, f of x1 here. Okay, so distance between this we can call delta something. Okay, so usually in this sum partition we need to define upper, that means supremum of this interval now. Okay, delta 1 is equal to f of x naught comma f of x1. Okay, so now from these intervals we need to identify supremum. Which one is our supremum now? See here, our graph is like this. So our upper sum or upper bound is f of x1. In this case here it is x1, f of x2 is here, and so on. So in this f of delta 2 is our f of x1 comma f of x2. In this case our upper bound is or supremum is f of x2 according to this function. Okay, so collection of all this delta n with supremum f of xn minus 1 comma f of xn, this is supremum of function is f of xn. Okay, collection of all this sum, that is summation delta supremum of summation of supremum of delta of xn, delta of x naught comma xn is equal to like delta 1 f of x1 plus delta 2 f of x2 and so on delta n f of xn. These all our supremum of this particular subintervals, right? So this sum is called upper sum, called upper sum of interval AB by using f of x, that is summation supremum of delta of x naught comma xn, that means supremum, that means upper sum. Is it clear? upper sum of interval. Okay, by using this upper sum of interval we can define upper sum of function also on particular interval. Okay, this is the concept. Okay, so next, so we need to define lower sum also. So same as usual, lower sum means you need to define the lower sum. That means x naught is over infimum here, again x1 is here infimum of this particular interval, and so on. Xr minus 1 is our infimum. So by using this concept we need to collect all these infimums. Now infimum of this interval is f of x naught is our infimum, f of x1 is our infimum, okay, f of x r xn minus 1 is our infimum. So collection of these all sum, okay, sum, you need to take sum of this. So a lower sum or lower bound partition over f, or you can define this UPF is equal to upper sum, LPF is equal to summation infimum of delta of x naught comma xn. Okay, so delta, here it is delta, this definition called lower sum of interval on AB. That means we need to just collect infimum of all these subintervals, we will get lower sum. And when we collect upper sum of this particular subintervals, we can get upper sum of this interval over the function, sorry, this function over the function over the interval AB. Okay, I hope you clear this concept. Okay, and thank you.